Our particle motion problems, particle motion objective. Particle motion problem deal with particles that are moving along the x-axis or y-axis, like they go horizontal or vertical. Speaking of horizontal, vertical, the position, velocity, acceleration of the particle motion are defined by functions, but the particle does not move along the graph of the function, it moves along an x-axis. So in this one objective, we are only talking about particle motion that goes horizontally, like it goes horizontal movement, x-axis. Okay, you guys can read all of that. Now, average and instantaneous velocity. Now, just remember, velocity means first derivative. That's the vocabulary word for the derivative. First derivative is also velocity. When it says instantaneous velocity, again a derivative. When it says average velocity, and if you remember, I said the word average always goes with a secant slope. So average velocity is secant slope. Instantaneous velocity is a derivative. Just the word velocity is also derivative. Just the word velocity is always derivative. Okay, first derivative. Now let's figure it out. Suppose P of t is a function which defines the position of a moving object at time t. Average velocity is equal average rate of change. You know that average rate of change means a velocity, average rate of change means, secant slope. So the word average comes, it means that's secant slope. Now, how do we do this? We're going to do, since they are talking about average velocity, so in the formula that we have f of b minus f of a, since now we are talking about position, average velocity means the average velocity of the position. So the position is going to go with the p of a minus p of b over a minus b. So you're taking average velocity of the position. So you make sure you understand what I'm saying. Average velocity means position, p of a, p of b. Now, instantaneous velocity, and I said the word instantaneous always a derivative, so it's gonna go p prime, like instantaneous velocity of the position. So remember the wording, average rate of average velocity means a secant slope of position, okay, p of t. So that's why we have a p of a minus p of b. Remember that. A particle position is given by the function pt e to the power t sine t, where p of t is measured in centimeters, t is measured in seconds. Answer the following questions. What is the average velocity on the interval t equal 1 to t equal 3 seconds? Indicate appropriate units of measure. Average velocity means that's a secant slope. Why I said secant slope? Because I know average means anything, average is secant. So I'm gonna go average velocity is equal p of 1 minus p of 3, because that's a position. We are taking average velocity of the position, 1 minus 3. When you plug in 1 in this equation, use a calculator. Plug in 3, use a calculator. Plug it in here in this original equation. And 1 minus 3, you subtract. Plug it in the calculator, you're going to get 0.274. What are the units? Since the units are talking about centimeter and t is measured in seconds, so it's going to be centimeter per second. That's for that. Now let's see. What is the instantaneous velocity of the particle at time t equal 1.5? Now instantaneous velocity, we know that's a derivative, but the word instantaneous also give me 100% derivative. So all I have to do is plug in, take the derivative of p prime, like p prime 1.5, plug it in. And we're going to use a calculator for this, but instead of calculator, I want to try it myself, take a derivative and plug it in. This is what we are looking for. So the original function is p of t equal e of t sine t. So let's take a derivative of this, and you know that's a product rule. If this is a product rule, that's f and that's a g. P prime t, go back there, p prime t equal, take the derivative of f, which is e of t. Et derivative is et times the derivative of the top, which is 1. Keep the g as it is, which is sine t. Plus, keep the f as it is and take the derivative of g, which is cosine t. You know that's a chain rule, but since t derivative is 1, it doesn't change. So this is what I got, p prime t. Now I'm going to fix it around. P prime t equal et sine t plus et and cosine t. Now I don't have to do anything. I'm going to plug in 1.5 and I'm going to use a calculator for that. E 1.5 sine 1.5 plus e 1.5 cosine 1.5. Plug all of this in the calculator. The answer would be 4.787, again centimeter per second. So this is how you get these questions for the position and the velocity. Before we proceed, a connection needs to be made when given a function f of x. How did we find the slope of the secant line on the interval from x equal a to x equal b in terms of position of a particle? To what does the slope of the secant line correspond? To what does the instantaneous velocity correspond? So we already know that slope of secant, I already told you that, is equal f of a minus f of b over a minus b. It means it goes both ways. Average velocity. Look at the connection. Average velocity. Slope of secant is this, and average velocity is also this. Then we have a slope of tangent line. Slope of tangent is equal f prime a and also instantaneous velocity. Okay, average instantaneous acceleration. Now we are talking about acceleration. So acceleration is always second derivative. Remember that. So if it's a second derivative, then instantaneous acceleration is my second derivative. Average acceleration, it's gonna go secant of what? If I have an average acceleration, then it means we are looking for a secant slope, because you know the word average goes with the secant slope of, if they are asking acceleration, I'm looking for a secant slope of velocity. So remember that. So let's try. If p of t is position, and p prime t is equal velocity, the velocity, then average acceleration is equal velocity of a minus velocity of b over a minus b. Remember, I never said position, right? So since they are asking average acceleration, with the average I know it's a secant slope, but acceleration, when I take the average when I'm looking for average acceleration, it means I have to have a secant slope of a velocity. Like, can you go back step one backward. So then I have instantaneous acceleration. It's gonna be v prime a, like you're taking a velocity is the first derivative. When you take a derivative of first derivative, don't you think it's gonna be second derivative? So that's what acceleration is, a second derivative. Or you can also make a notation p double prime a, like you're taking a position second derivative. When you have a velocity of a, then velocity of a means when you take a derivative of velocity, it's a second derivative. So this is how the notation goes. So let's try these questions. A particle position is given by function p of t, et sine t, where p of t is measured in centimeter, t is measured in seconds. Answer the following questions. What is the average acceleration on the interval t equal 1 to t equal 3? Now they said average, which means that's a secant. Acceleration. If I'm looking for average acceleration, actually I'm looking a secant slope of a velocity. I just write that small velocity here. So I'm going to go average acceleration, and it means I can write the notation. I can write as an average acceleration. I can also write p, it's going to be average acceleration. It's going to be p double prime t, or it's v prime t. So you can use any one of those notations. When you see v, it means velocity. That's the first derivative, but when you put the prime up on top of it, that's a second derivative. So now how do I do that? It's going to give me v of 1 minus v of 3, because I'm looking for acceleration, double prime, 1 minus 3. When you plug in, I don't have a velocity here. Look at this. This is the original position. So I have to get the velocity function, and I plug in 1 and 3. So let's take a derivative of that. So I'm going to go p prime t, or you can say v of t. Either way is good notations. This is a product rule, f of g. So if I take a derivative of this, it's going to give me, and we actually got the derivative in the first question already, and it was somewhere over here. This is p prime t et sine t. So I'm going to go, let's see. I'm going to go p e t sine t plus et sine t, and I have plus et cosine t plus et cosine t. So that's my derivative. We already have that. Now I'm going to plug in 1 in 3 in this v of t, and it will give me the answer negative 10.403. Then it's going to be centimeter per second. These are my units, but you do understand I am taking a second derivative. It's going to be square. Like if we did one time, it's going to centimeter per second and then per second. So that's 2 seconds, like twice. So this is what we got from this. That's the answer. What is instantaneous acceleration of the particle at t equal 1.5? So the original position is p of t is e of t sine t. That's my original position. I have to get the instantaneous acceleration means second derivative. So I have to take a first derivative, and then we have to take a second derivative. So I already know my first derivative is this. It's et sine t plus e of t cosine t. That's my first derivative. Now I'm going to get the second derivative. So your notation is going to go v prime t. Or you can do p double prime t. Either way is good. Since I'm going in order, I'm going to go v prime t. So this is a product rule. This is a product rule. So let's do the product rule for this. This is f, that's g. So take a derivative of f, which is going to give me e of t times the derivative of t, which is 1. Sine of t, like a g, is going to stay as it is. Plus f is going to stay as it is. And the sine t derivative is cosine t. Done. This is done for this position. Then I have a plus, and I have to get the I have to get the derivative of this, ft. That's again my product rule. So et times 1. Then cosine t is going to stay as it is, minus, or just make it plus, e of t stays as it is, and cosine derivative is negative sine t. T derivative is 1. So here we go. That's all we have. So let's try fixing around. V prime t. I have e of t sine t. This one is okay. E of t cosine t. Then I have a plus e of t cosine t. And I have a negative, because positive and negative is negative, e of t sine t. So this whole thing I got. What are you supposed to do after this? Plug in 1.5, because that's what they're asking me. They said V prime 1.5. So you're going to plug in wherever you see the teeth, 1.5, plug it in the calculator, and your answer is 0.634 centimeter per second square. So this is the answer for this question. Okay, let's correlate the concepts of position, velocity, and acceleration to what we already know about a function and its first and second derivative. So I'm going to say f of x corresponds with position. Like position is always original function. So I'm going to write this is position. Next, this is f prime x corresponds with either p prime t, like a first derivative of the position, or another notation we can use a velocity, and make sure you don't put the prime on top of velocity, because velocity is first derivative already. So equal velocity. F double prime x corresponds with p double prime t, like the second derivative of the position, or you can say v prime t, like a second derivative. Velocity is first derivative. When you take a derivative one more time of the velocity, it's going to be second derivative, or you can do a of t. And this is equal acceleration. Okay, let's summarize our relationships between position, velocity, and acceleration. So if velocity, like a first derivative, is equal 0 or undefined, then what is that? We already know velocity means a first derivative, like it's the speed with the direction. So this is what velocity is. If velocity is 0 or undefined, then we're going to say potential change in direction of the moving object, So that's a position, motion of the particle we are talking about. So we have to say that change in direction. So velocity deals with the first derivative, instantaneous velocity also first derivative, and derivative where the direction is, and velocity also giving us a direction. So if velocity is greater than 0, then we're going to say position is increasing or we can say particle is moving to the right. If you guys remember, we did first derivative. We said first derivative means relates to, when we see first derivative, it means increase, decrease, and relative extrema. That's what the first derivative was. And for increase, decrease, we make the derivative equal 0. For relative extrema, increase, decrease, everything up here. How do we solve them? We make derivative equal 0. We get critical points. We make sign chart. When we make sign chart, we have positives and negatives, for example. 0 is my critical point. A positive and negative. So I'm going to say it's increasing from negative infinity to 0, decreasing from 0 to positive infinity. But in a case of motion particle motion, we're going to say particle is moving to the right. Like I'm going to say that's right. Particle is moving to the left. So negative is left, positive is right. So that's what it is. Since this is positive and that's negative. If the velocity is less than 0, then we're going to say position is decreasing or vice versa, like you can do either particle moving to the right or position is increasing. So we're going to say particle is moving to the left. Moving to the left. Changes from positive to negative. If that was the first derivative, changes from positive to negative, it was relative maximum, right? But since we are talking about a velocity, then we're going to say particle is moving from right to left. So I'm going to say particle changes from particle changes direction moving from right to left, positive to negative. This one changes from negative to positive. We would say if that was the first derivative, then we would say, okay, that's relative minimum because it's going negative to positive. But in this case, we're going to say particle changes direction from left to right. Okay, let's compare acceleration and velocity. It's like a second derivative and first derivative. So if second derivative, that's a second derivative, that's a first derivative. So if acceleration is 0 or undefined, then we're gonna say change in signs of velocity. We can say change in signs of velocity. If the acceleration is greater than 0 positive, you know when we had a double prime, and if its double prime is positive, then it's concave up. If double prime is negative, it's concave down. So in this case, since we're talking about velocity, we're going to say if it's increasing. Velocity is increasing if the double prime is greater than 0. If double prime is less than 0, which is negative, then it means velocity is decreasing. Changes from positive to negative, we're going to say it's changes from increase to decrease. This one changes from decrease to increase. Okay, let's do some examples. The graph below represents the position s of t of a particle, which is s of t means it's a position, it's an original function of a particle which is moving along the x-axis. So this is my original s of t. That's s of t. At which points is the velocity equal to 0? Velocity equal to 0. What is velocity? Velocity is the first derivative, isn't it? Velocity is first derivative. So when or where the derivative is 0. Since this is my original position, this is my original function, then how can I find the derivative for this? I'm going to draw tangent lines. So draw tangent line here, over here, 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 and here. So I can say where my tangent line is equal 0 at B and D. So I'm going to say velocity is equal 0 at T equal B and T equal D, because my tangent lines are straight, they are horizontal. Because I'm gonna give them justification, because you know always justification when we write because, after because we always mention whatever is given. So I'm gonna say because s of t changes direction at velocity is equal 0 when the st changes direction. You can tell it's changing direction at B and D because this is all positive, this is all negative. So at B it changes direction, at D it changes direction. So it's true. At which points does the acceleration equal 0? So acceleration means that's a second derivative I'm talking about. Like let's use, this is a second derivative. And you do understand second derivative deals with concave up and concave down. So and also point of inflection. So how do I say if acceleration is equal 0? Acceleration is always equal 0, then it gives me point of inflection, and then we make a sign chart, right? So when my acceleration is equal, it means I'm looking for a point of inflection. So I'm going to say acceleration is equal 0, where acceleration is equal. And what is actually point of inflection? Where the concavity is changing. So look in this graph, I have this concave down up here. From there, my graph goes concave up. So C is the point where the concavity is changing, where it's my point of inflection, where the derivative, second derivative is equal 0. So acceleration is 0 at t equals C, because again S of t has a point of inflection. There. Next, on what interval is the particle's velocity is positive? I mean, you can tell I already marked them positive, negative, positive. So at what intervals is intervals, like the whole interval they are talking about? So I'm going to say where it's positive. So I'm going to say this one is the arrow goes in this direction, like all the way in this one. So I'm going to say velocity is greater than 0 on intervals. Okay, intervals. So I'm gonna say it's positive on 0 to b. Why I didn't say negative infinity or positive infinity? Because this graph, for example, let me check if this graph, yeah, it is going forever in this direction. So it is going forever in this direction, like an arrow. So I'm gonna say velocity is positive on 0 to 0 and b. I mean 0b, yes, starting from 0 to b, and d to positive infinity. I mean, you can tell d to positive infinity. It's this one. So this is all going positive, and this is what it is. Next. And justify, because S of t is increasing. Next one, what interval is the velocity is negative, which means less than 0? I can tell from b to d, that's where it's less than 0. So velocity is less than 0 on bd because st is decreasing. On what interval is the particle's acceleration is positive? Acceleration means it's a second derivative, and positive means it's concave up. So where it's concave up, I'm going to say it's concave up on c to positive infinity, it's concave up. So I'm going to say acceleration is greater than 0 on c to infinity because S of t is concave up. There. Next one, on what intervals is the particle acceleration is negative, which means less than 0. So acceleration is less than 0, like second derivative, which means concave down. So it's concave down 0 to c because st is concave down. It's 0 to c, from here to here, it's concave down. So this is so far for that. Next, we have 5 commandments of particle motion, and you guys have to really memorize those and make sure that it makes sense to you guys. So, and particle motion means I'm talking about horizontal motion. I said that before. It's a horizontal motion. The first commandment says, if the velocity is positive, then object is moving to the right. There. Next, if the velocity is negative, like the first derivative is negative, then object is moving to the left. The speed, this is very important. I'm going to make star with it. That's important. The, what did I say? The speed is increasing when the signs of velocity and acceleration are the same. So what does that mean? Okay, I'm gonna write here, look at up here guys, speed increases when acceleration and velocity has the same signs. For example, they have positive and positive, or they have negative and negative. If they have the same signs, it's increasing. Next, the speed is decreasing when the sign of velocity and acceleration are different or opposite, like one positive, one negative. Then it means speed is decreasing. The fifth one, if the velocity, like this first derivative, is equal 0, but the acceleration is not equal 0, then the object is momentarily stopped and changing direction. Okay, that's what it means. Okay, let's do some examples. Suppose the velocity of the particle is given by the function this for t greater or equal 0, where t is measured in minutes, t is measured in inches per minute. Answer the question that follow. Find the values of v of 3 and v prime 3. Based on these values, describe the speed of the particle at t equal 3. And we already know that speed of the particle means acceleration and velocity have same or different signs. Now, what is v prime means? That's acceleration. What is vt? Of course, that's a first derivative. So this is all that we have. So let's find out the value v of 3. Since v function is already given, all I have to do is plug in that 3 there. So I'm going to plug in v of 3 in the equation, the function that they have right here. 3 plus 2 whole squared, 3 plus 4 whole squared. Oh, this one is not squared. Okay, so I got that, and let's try. This is 5, and I got 49, because 4, 5, 6, 7 squared is 49. The answer is 245 inches per minute. Which is right here. Now, v prime 3, which means I have to take a derivative of this and then plug in 3. So, you know, that's a second derivative or acceleration, or I can say v prime t. So let's do the derivative. And this is actually a product rule. And up here, this portion is my chain rule. So this is my f, that's my g, like a product rule. So take the derivative of f, which is 1. Keep the g as it is, which is t plus 4 whole squared, plus keep the f as it is, which is t plus 2, and take the derivative of t plus 4 whole squared, which is a chain rule. So for the chain rule, I'm gonna make a bracket so I can show you the chain rule. 2 jump to the front, keep the inside as it is, which is t plus 4. 2 subtract 1 is 1 times the derivative of inside, which is 1. And that's my chain rule. So this is what we got here. Next, let's fix it around, or probably distribute that too, something like that. So let's try that. So I'm going to go v prime t equal t plus 4 whole squared. I'm going to keep that as it is. I don't want to solve or FOIL this because, you know, I have to just plug in 3 there. So I don't want to waste time on that, but I just have to fix this just a little bit. This 2 goes to the front. Then I have t plus 2 and I have t plus 4. There. Now plug in 3 there. So v prime 3. So I'm going to go 3 plus 4 whole squared. I got plus 2 and 3 plus 2. And I have a 3 plus 4. Okay. Now when you solve this, it's going to give me 119 inches per minute squared, but because it's a double prime, if you guys remember. Now I'm done with everything. Based on these values, describe the speed of the particle. Now, speed, acceleration, and velocity signs. So if you check, this is positive and also that one positive. If the acceleration and the velocity signs are exactly the same, then it means the speed is increasing. So I'm gonna say, since v prime 3 is greater than 0 and v of 3 is greater than 0, v prime 3 is also greater than 0, then the speed is increasing at t equal 3. And that's my explanation for that one. Okay, next one said, part B, on what intervals is the particle moving to the left? Right, show your analysis and justify your answer. Left, right, I already told you left, right means if I make a sign chart, then positive will tell me I'm going right, negative will tell me I'm going left. So in direction, always the velocity is the one giving me direction. So since velocity function is already there, like this is my velocity function, v of t equal t plus 2, it's up there, right there, this is given. Then I have a t plus 4 whole squared. All I have to do to make a sign chart for left and right, so I have to make this equal 0. You know that derivative equals 0, critical points, and then sign chart. So I have to make it this equal 0. I will make each one of them equal 0. T plus 2 equals 0 and t plus 4 whole squared equals 0. T plus 2 is going to give me t equal negative 2. This one is going to give me t equal negative 4. And you know, for the square, I can square root this, they will cancel out. I'm left with t plus 4. So I got t equal negative 4. That's the next one. So let's figure it out. Which ones are my critical points? This is t plus 2 is negative 2, and that's this one. Okay, so we are making a sign chart, and for the sign chart, negative 2 and negative 4. So I'm gonna make, and they said t is equal greater than 0. If it's greater than 0, then it means that's a 0, and I'm only talking about this portion. These are my critical points. Negative 2, negative 4 is not going to work because for the restrictions, it says t is greater than 0. So I'm going to make it 0, just a 0, and that's greater than, everything greater than 0, like that. So pick, probably make t equal 3, because that's what they are asking me anyway the whole time, right there. So I'm going to say plug in 3 in here. 3 plus 2 is 5. 3 plus 4 is 7, 49, and it's going to give me positive. The whole thing is going to be positive. So it means for t greater equal 0, v of t is always greater than is always greater than 0, so the particle is always moving to the right, so that's how my critical points doesn't work for me. I already explained that, because the t greater than 0, that's my restriction. Both of them are less than 0, so I just picked t greater than 0 and I picked 3. You can pick any other number, it will give you the same thing. It's going to go positive. If you guys have any questions, please comment below and I will try my best to answer. Also, I'm gonna make a video on free response questions on the particle motion, so you guys can watch that too.